Hello everyone, I'm Chanjana, a final year student from APET. My research title is Explainable AI Agent-Based Decision Support for Predicting Shipment Delays in Supply Chain. So, supply chain simply refers to the entire product cycle, starting from raw materials to the customer delivery and the payments. And often, when there is a delay in shipment, we are led to financial losses and customer dissatisfaction. Again, poor delivery reliability also risks us from losing partnerships with our retailers and distributors. In the research, in the current research, despite the significant advancement in machine learning in shipment delay predictions, supply chain is yet to fully diverge into the field of AI and autonomous agents. This is mainly due to the employees and managers hesitate to trust AI decisions without clear reasoning. Therefore, the problem statement for this research is the lack of accurate and interpretable predictions of shipment delays to support agent-based decision support systems. The motivation is to develop a feasible AI solution to predict shipment delays. Without further ado, let's move on to the comparative analysis of this research. So first, to evidence that EBM model is suitable, I've taken the smart logistics supply chain dataset and I have done a few of the data pre-processing techniques, mainly looked into the sum of null values, and then I also created the timestamp due to feature engineering. And here we have our targeted um, we created a new targeted variable shipment delay, and that is based on the shipment status, which is in three categories: delayed, delivered, and in transit. So for in transit, I have replaced it with the logistic delay variables, and I've removed the unnecessary features like logistic delay, the asset IDs, and the misleading ones like the logistic delay reason and the shipment status. And again, I have split the data set and then I have trained my EBM model, and this is the result that I've gotten for my pilot test run. So we have a 65% accuracy with a 49 recall for delay predicting delays and a ROC of 0.64. So this is the EBM result. And so in my comparative analysis, the approach that I've taken is, so same data set, and I have taken in some candidate black box models and candidate interpretable models. So to evidence that EBM is suitable to represent the interpretable model class, I've compared it with the interpretable models. So if you see that this has 65% and the EBM models that I have gone through, I tested GAM. So GAM has 52% accuracy, and rule fit has 61%, and decision tree has 58%. So you can see that EBM is is the most accurate interpretable models for this data set. Whereas when we look into the black box, here for random forest gradient boosting, XGBoost, ANN, and SVM, I have also applied one hot encoding. And the results that we have observed is that random forest is at 67%, and gradient boosting 62%, XGBoost at 61%, ANN at 61%, and SVM at 68%. Again, I've also looked into the cat boost, so that is also at 68%. So what cat boost does not require the one hot encoding. And so with these results, the final conclusion is that cat boost and SVM has given us really good performance, right? And but when we go to apply, so from from recall, like there's a slight margin change from the cat boost results to SVM. But then again, when we go to apply the SHAP explanation, SVM had a lot of fallback as we cannot use tree explainer. We had to use kernel explainer, which has a lot of computational overload and it takes a lot of time. When tested, it took me 3 minutes and 46 seconds, whereas Casbo's it was around just 30 seconds, right? So yes, SVM is a slightly better performing, but considering the interpretability, the best solution, the best candidate to represent for the final comparative analysis with EBM would be CatBoost. And therefore, I've taken CatBoost as my candidate for the black box. And then based on performance, CatBoost does have a 3% margin on accuracy. And then we also looked into the global explanation, and you can see we have feature pairs also, how they correlate with the final target and how the predictions are like. So this shows the feature importance, right? So traffic status is the highest of important feature. And again, if we look into the cat boost, also you can see even though it doesn't show feature pairs, traffic status, inventory level, and latitude. So both models have prioritized in these three layers, these three features. And if we also look into the local instances, so again, for the first instance, you can see that both classes have predicted it wrong, right? Both classes predicted the class wrong. They predicted it as not a delay because of the traffic is being clear. So the con so you might think that cat boost is this thing, but some researchers still have argued that interpretable models are transparent, right? Whereas post hoc models is not. Even though it gives us an explanation, it still behaves as a black box model. So there is a lot of confusion in trust and transparency, and I have mentioned all of this in my literature review under the limitations of post hoc XAI. And therefore, considering a scenario, we could think of a scenario where simply a worker tells you why they did it, whereas another instance, a worker gives you a result and the manager tells you why the worker got this results, right? So the first instance is always more feasible and easy to utilize. And when it comes to our AI agents, so what we'll be aiming in this research is to get the EBM model. So to build an AI agent based on an LLM, a local LLM like Olama, and to allow it to reason out. So once a user gives a prediction, so we can start a new chat. And once the user gives a prediction value, it takes the value, it validates that data, and then it gives it feed it to the EBM model, the trained EBM model with all the feature engineering and such, and it will give us a result. So initially in my development, I was working with a smart supply chain data set, which was a different data set. And I had issues where there was very low correlations with the target variable, around 0.00 percentage, and my model results were really low. It was 0.51, which is just random guessing. So I couldn't really work with it. So I had to look in for other data sets, and I came across this data set. So this development was done for the previous data set because I wanted to get an idea on the development aspect of things to see if there is any issues with integrating the EBM model with the LangGraph AI agent. And so EBM model, the interpret class was only available on Python. an older version of Python. So, but Landgraph did is compatible with it, so there wasn't any issues. So we'll be changing all of this data set, but you can see that you get the results, and you can also get the feature importance and how it affected. So this explanation is clear, and then we can also ask them to send us an email. Uh, so in the future work, we'll be further developing this AI agent, and we'll make sure the UI is properly done, and the email notification with the mailbox is also done. For now, you can draft your email, and if you're satisfied with it, you can proceed. And that would be the end of this demo. Thank you.